Bienvenido a un nuevo contenido de Uninorteco. No olvides suscribirte a nuestro canal.
Welcome everyone to a new session of PiA webinar series. Today is on a special occasion. Therefore, we have a very special guest today because it has been a year since our first webinar. So before introducing her, I want to remember that PiA, Particles in the America, is a joint initiative supported by the Asociación Argentina de Sedimentología, SINSTAC from Mexico, Instituto Argentino de Oceanografía, Instituto Geofísico del Perú, Mississippi State University from the United States, Universidad de la República from Uruguay, Universidad Federal do Espírito Santo from Brazil, Universidad de Costa Rica from Costa Rica, Universidad del Norte from Colombia, Universidad Técnica Federico Santa María from Chile, Sequoia Scientific Inc. from the United States. I want also remember you that you can visit our webpage to get information about PiA activities, including the past recording of the webinar. Today, we are happy to present Professor Jaya Sivitsky, which is going to talk about Earth's sediment cycle during the Anthropocenes. Professor Jaya Sivitsky received doctoral degrees, oceanography and geological science from the University of British Columbia in 1988. She is emeritus professor at the University of Colorado at Boulder. She has over 500 publications, including authorships or co-authorships of 65 peer-reviewed books, and has served in various editorial positions for many international journals. She has taken leadership roles in large international projects. Professor Sivitsky works in the forefront of computational geoscience, sediment transport, land-ocean interaction, and Earth surface dynamics. She is presently Executive Director of the Community Surface Dynamics Modeling System, an international effort in 680 countries to develop, support, and disseminate integrated computer model to the broader geoscience community. She is a fellow of the American Geophysical Union and received the Royal Society of Canada Huntsman Medal for Outstanding Achievement in Marine Science, the EPM Francis Shepherd Medal, and an Honorary Doctor of Science in Sustainability from Newcastle University. This is a very short resume of his CV. I just can say that she is one of the most well-known and reputed researcher in her field with several seminal papers. So we are very glad to have Professor Sivitsky during this session of PiA webinar. So Professor Sivitsky, welcome, and it's a pleasure for us having you here. So now you can present your talk.
Well, thank you. And thanks to everyone for showing up and hearing my presentation. This will be a review of the Earth's sediment cycle. And during a new geological epoch, the Anthropocene, and the pictures you see on your screen, I'm going to walk you through how we arrive at these numbers. In the top of the screen, it says Anthropocene Land to Sea Sediment Flux 2010. And I'm going to talk about the difference between the amount of sediment that moves from land into the ocean in 1950 and compared to 2010. And in the bottom of your right side of your screen, you will see it says Anthropocene sediment loads. And in there, you'll see mining and construction and soil erosion. And you will also see this land to sea flux. And so I will be talking about both the upper diagram and the lower diagram, including global change and climate change and how that impacts these numbers. And I was asked to write a review of this, and the authors you see listed beneath my name are my co-authors on a Nature review paper that is in the final stages of being published. So that's the presentation for today. So the first slide is a map of the world, because we're talking about a global sediment cycle. And one of the ways we can talk about a sediment cycle that makes sense is to talk about the sediment that leaves the land and enters the ocean. Gravity moves this material offshore, and once it's offshore, not very often does it come back onshore. I mean, there can be very small amounts. Hurricanes can move sediment back onshore. But in the great scheme of things, that's a very small amount. So the sediment cycle usually is considered over very long periods of time. And so we're interested in what this volume of sediment, this massive sediment. And the unit we use is GT per Y, gigatons per year. And 1 gigaton per year, that's 1 billion or 1 gigaton metric tons. And so a lot of people have a hard time understanding conceptually what this means. And so I've come up with this method of doing that. The Great Wall of China, at over almost 9,000 kilometers in length, 6.5 meters in height, 4.5 meters in width on average, is cubic kilometers of about 0.26. And that's equal to about 0.4 gigatons if you use a typical density for that conversion. And so 1 gigaton is equal to 2.5 Great Walls of China. So you're going to hear a lot about gigatons, and I want you to know sort of conceptually in your head, and also to understand this is per year. So this is gigatons per year that is being moved. The other concept that I think we should clear up before I begin my talk is the Anthropocene. Now, the Holocene is a period of time. It's the epoch leading up to the Anthropocene. It's about 11,700 years. And its dynamics of the surface of the planet is based on the Milankovitch cycles. And these are the eccentricity, obliquity of how the planet behaves as it circles the sun over geological time. And so the Holocene was driven by our planetary motions that sort of control the amount of sunlight that any one part of the Earth receives in a year. And the Anthropocene is not driven by that anymore. Now that's, the Milankovitch still goes on, but the drivers are now humans drivers, population, energy consumption, and global productivity. And that may not seem obvious to you. And so I'm going to show you another slide why that is the case. And this slide shows you 6 parameters, like how much reservoir capacity behind dams and how linearly that tracks with global energy consumption, or how much CO2 is in the atmosphere and how that tracks so linearly with energy consumption. And the same for plastic production or cement production, linearly tracks almost perfectly with the global GDP, gross domestic product. And the same with copper production or ammonia production, they track almost linearly with human population. So it's because these drivers of our environment track so perfectly with these other three forcing functions that we usually consider that population, energy consumption, and productivity are really part of what makes up the Anthropocene. So let's begin with what is the terrestrial flux of the landscape. So if we looked at a geological eon, the Phanerozoic, the eon of life, it's about 541 million years long. And on average, the flux off the land into the ocean is about 5 gigatons per year. So the Quaternary period, the last 2.58 million years, that has a terrestrial flux of 11.4 gigatons per year. And you'll notice it's more than double the Phanerozoic average. And many studies have confirmed that. And it's really because Quaternary is a little different than those previous times because of glaciation, the growth and retreat of large ice sheets. And it's because of that that these studies have considered that it is a bit of an unusual time in that long period because the Quaternary is part of the Phanerozoic. So if we look at the Holocene, that can be broken up into two units. The deglacial period, it's about 5,000 years, and that's when these big ice sheets were melting. And the amount of sediment coming off the landscape, it's double the Quaternary average, and it's about 22. So it's a short burst, 5,000 years long, really releasing a lot of sediment. And then you have this post-glacial period, and it's back to the Quaternary average of about 11 gigatons per year. And so that pretty much takes us up to about 1950 when the Anthropocene begun. And there were two studies. Hook wrote a paper in 2000 and Wilkinson wrote a paper in 2005. And although they didn't really specify when in the Anthropocene, they considered that the terrestrial flux was shot up to about 75 gigatons per year. So if you look at these numbers, you say to yourself, well, how's that even possible? And so we did look in this nature review that we did, we looked at these numbers carefully. We got numbers for around plus or minus 10 years around 1950 and plus or minus 10 years around 2010. And we confirmed the 75, our number is 73 gigatons per year for 1950. But the number for 2010 is just enormous. It's 328. And so this talk is to tell you how that occurred. And really how we're in a totally different planet than we once were. So first off, we're going to start with rivers. Rivers send a lot of sediment down to the ocean, dissolved load, bed load, suspended load. And in this diagram, I'm really showing you about the suspended load, the bed load. In other words, the particles, the suspended particles. And Milliman and Mead in 1983, they wrote a paper and they calculated that around 15 gigatons per year were being delivered to the ocean, scaling up the information they received from these 70 rivers that they studied. In 1992, Milliman and myself, we wrote a paper and we did the same kind of analysis, and we got a number that was about 20 gigatons per year. And we had about 280 rivers that had reasonable data. And we used data for that study that was largely before dams were being globally constructed in a big way around the world. So it's a good value for around the sort of 1950 period. Well, I continued this and wrote another paper in Science that we were able to use water balance modeling, and we applied it to about 4,000 rivers. And the values we got for this particulate low was between 14.1 and 15.5 gigatons per year. And our calibration rivers were around 340, so an increase a bit. I wrote another paper in 2011 with more calibration rivers, and we got slightly different numbers, and we modeled more river basins. We put out another study in 2019, more rivers, and now we include Greenland because we never used to include Greenland, and I will talk about Greenland later on. And then this study, we went back, we updated our observations, and you'll notice that the amount of particulate sediment going to the ocean is greatly reduced from all the previous studies. It's now down to 7.5. So in order to understand those numbers, I want you to look at these two diagrams. Let's start with the one on the right. It's water discharge in cubic meters per second. And you'll notice that in terms of the landscape, there are a little over 11,000 rivers. And of those 11,000 rivers, about 1,121 of them, or 10%, they account for 90% of the freshwater discharge to the ocean. So there may be a lot of rivers in the world, but only about 1,000 of them are significant. And even to go from 90 to 95% discharge into the ocean, you would have to double the number of rivers just to get that 5% extra. And so all these low order streams, they don't deliver very much. There's a lot of them, but they don't deliver much river. And this is even magnified if you looked at the sediment discharge in kilograms per second. And you'll see that 90% of the sediment that goes to the ocean only comes from 454 rivers. And to get that extra 5%, you'd have to double the number of rivers again. So knowing sort of how the planet works is really important when you're doing global studies. Now, if you were to look at the Anthropocene record, you would be focusing on the graphs that show up in brown on this diagram. And here we've got 4 rivers that are medium to large size rivers that drain, big scale mountains, and they're carry a lot of sediment. The Godavari in India, the Yellow River of China, the Red River of Vietnam, and the Yangtze River of China. And if you were to look at the Holocene record, based on deposits that have been mapped, cored, dated, studied, and converted to sediment loads, millions of tons per year in those cases, you'll see that sediment started. The Yangtze is the only long one, and you can see that deglacial signal, and then you'll see it starting to rise up. And that rise up is because of humans. So the human story can be detected back a couple, 2,000, 3,000, 4,000 years So even though the Anthropocene starts in 1950, that does not mean that's done for convenience of how the Commission on Stratigraphy works. But that doesn't mean there isn't a human influence that could be detected back then. And so it can be detected back then, but what you're seeing now in the brown is you're seeing these great reductions in the flux of sediment to the coastal ocean. And in this case, it's because of dams. So this leads us to this figure on the land-sea flux. Now, these are considered natural processes, but these natural processes have been hugely impacted by humans. And so we don't know much about whether alien transport is increasing or decreasing over the last 70 years. We only have an ability to estimate sort of what the global flux is. It's about 1.5 gigatons per year that of wind transported sediment that enters the ocean. But when it comes to river transport, fluvial transport, we've never seen such a small amount of sediment enter the ocean. We're back almost to the Quaternary average, and most of that is because of dams. So the suspended load has been cut in half. It's now down to 7.2 gigatons per year. Bed load, which used to be about 1 gigaton per year, is now down to 0.3. And that's from riverbed mining and less water that reaches the ocean. And then there's the dissolved load. Now that's decreased a bit that we know of, but I think more work needs to be done on that. And then you have the particulate organic carbon, 0.2%, and we do not have the studies to know how those trends are changing. We know coastal erosion is increasing, but we don't know by how much. And that's very complicated. And if you want to talk about that, I'd love to talk to you about it. And the subglacial meltwater flux has increased, and so is the iceberg flux increased. And that's largely because the areas that have been glaciated are now going through a rapid deglaciation, including Antarctica and Greenland, Alaska, northern Canada, etc. Anyways, the total flux for 2010 is 17.3. So just to summarize what I just said, but having some other pictures for you to look at, we know the iceberg flux is increased, and it's gone from 0.7 to 3 gigatons per year. So that's offsetting the decrease in suspended load. That's gone from 14.5 to 7.2. So it wasn't for this offset, it would even be more of a decrease than you're now seeing on the bottom of the screen from 1950 and 2010, 22.4 to 17.3. Subglacial meltwaters also increased from 0.2 to 1. We don't know much about the trends in wind. We don't know much about the trends in organic carbon. We don't really know much about the trends in the dissolved load, and we'd love to know and don't know much about the trends in waves and tides. We're pretty sure that we've got the reasonable ballpark estimates of the numbers, the bulk numbers, but we don't know the trends. So let me just go over and sort of flesh that out a bit. So here's two maps. This is from a paper that we're just now writing. So this is fresh off the presses that hasn't even been reviewed. And we've got bed load on the top, and we've got suspended load on the bottom. And these kinds of models, we model every single day. And we're modeling about, I forget how many, about 11,700 pixels around the 11 by 11 kilometer pixels around the world. We model daily. We typically model for 30 years. In this case, we modeled for 60 years daily. The first 30 years, we considered that just spin up of the model. What else should I say? And so the bed load map, you see, this is the first time anyone's ever seen such a map. And we're just starting to realize, you know, what are the driving forces behind bed load? Well, there's the amount of water and its velocity, shear stress, and also the slope of the land that translates often to hydraulic slope. And so those are the two big drivers, and grain size too, but those are the three big drivers of bed load. And suspended load, that is, I guess you all are experts in this, so I'll just remind you, it's wash load and it's suspended bed material load. And so these two combine to give you the suspended load. And so we're pretty good at the suspended load. We're just entering to be relatively good at the bed load, but we've still got tons of work to do on that. And to do the bed load, we had to put a lot of effort into river slopes. And that has probably been one of the fastest areas of being improved, is our understanding of river slopes. And it's very tricky when you model it, because when you're modeling at 11 by 11 kilometer grid scale, you have to downscale the river channel, and you have to do that in a very sophisticated way. And we're just now learning how to do that. Particle size, well, we had to figure out what the particle size in all these rivers, and we had to come up with methods to predict it, and then we have to see how well we could predict it, and we had to incorporate it in the models. And again, that was a lot of work. And if you didn't do slope and particle size, you can never do bed load. At least on a global scale, I should say, at least on a global scale. So let me summarize that for you. So we've been showing you these maps. How does that translate into the big picture? Well, you've got a number of columns here: drainage area, water discharge. But the sediment load for 1950, that is both suspended and bed load, in other words, the particulate solid load, the mass that you're carrying of solid particles in the water. Back in 1950, all evidence suggests that's about 15.7 gigatons per year. Now you see that big drop in 2010 to 8.5 gigatons per year. So, and that shows up so that in Australia, you don't have that big a decrease, but in Africa, Asia, particularly Europe, Indonesia, it was only some recent dams that are starting to impact Indonesia and Papua New Guinea and places like that. North America had a big drop, South America. And then you have this new area, Greenland, that we never knew about, that is increasing in its flux. So let me give you one example that would sort of wrap your head around this. Now, I've been working with my colleagues in China for many years, and because they have such a lovely database. It's a great area to work in, to test ideas out, because they've really got a lot of good information on how much dams are trapping sediment, how much sediment is being carried in by the main river systems. So it's a really good database. And what we've noticed is that there's been an 84% decline in the amount of sediment entering the ocean in the last 70 years. It's remarkable, this decrease. So the almost 2,000 million tons per year, or 2 gigatons per year, 1954 to 1968, dropping all the way down to today, where it's closer to 310 million tons per year. We know which dams are trapping the sediment. And even though they're experimenting around with amount of how they operate these dams, they release sediment in the dams now, and they're really experimenting and doing great things and trying to get more sediment to the coast. You still have this remarkable drop in the flux of sediment to the coastal ocean. And globally, large dams are now intercepting most of the major flow into the ocean. The amount of reservoir capacity before 1850 was 6.1 cubic kilometers. It grew 2 orders of magnitude between 1850 and 1950 to 685 cubic kilometers. And now it's up to 15,000 cubic kilometers, the reservoir capacity of these large dams. And they've trapped, remember, 1 gigaton is equal to 2.4 Great Walls of China or something like that. These large dams have trapped 3,200 gigatons of sediment since 1950, an amount of sediment that is just unbelievable, that is now being stored on land in dams. And these maps that you see, this is the US, and these are both some moderate size as well as large dams. So there's both sizes of dams in this diagram. You can see the history of, in this case, colonization of Europeans' colonization of Americas, and how they migrated across the country and then rapidly industrialized the continent. And I'm showing the satellite image that we processed to really highlight the amount of reservoirs in this particular area of southern US. So we've simplified it. You only can see land as sort of a yellow-orange, and you see the reservoir showing up as black or blue, the blue being higher suspended sediment in the reservoirs. You also see the Mississippi River snake down towards the Mississippi Delta, and there are some small oxbow lakes that are natural along that Mississippi Valley, but most of the water you see in that picture is from reservoirs. We've altered the landscape because of dams. And so now I'd like to take you to that next part of the story, which is both the production and consumption of sediment, because that's where I think the real big story is. We've talked about dams and how important they are in consuming sediment. If these dams were all taken down and the sediment was allowed to flow to the ocean, then that consumption would turn into production. So free waste, they consume sediment. Cement consumes sediment. And then you have the various types of mining that supply sediment. Soil erosion is a form of sediment production or supply, largely because we really handle our agricultural lands very poorly. And so we can look at these numbers of soil erosion, and you can see that global soil erosion was quite large already in 1950, and it is still much larger today. Global construction, much higher. Mining and the waste products from mining is remarkably high. Global aggregate production has shot up hugely, largely because of cement production. Sand and gravel mining in coast, we're not so sure about this number. We're still looking into it. But it looks like it's shot up enormously. And most rivers are now having some level of mining of the sand and gravel. And so you can see that that has shot up from 46.6 to 288.5, a 519% increase. And if you looked at the consumption, you know, you've got what's stored in the reservoirs. We now store 65 gigatons per year. This is all per year. This is in gigatons per year. 65 gigatons per year. An unbelievable amount of sediment is now being stored in reservoirs. We have the highway consumption, coal consumption, and concrete consumption. And this concrete, the remarkable thing there is that one country accounts for more than 90% now, and it's China. So, you know, they're the large consumers of sand and gravel for cement production or concrete production. And just to give you an example of how we do these calculations, it takes roughly 1.25 gigatons of sand and 1.9 gigatons of gravel to make 1 road kilometer. You have 64 million kilometers of global roads and highways. You do the math and you get around 200 gigatons have been consumed of sand and gravel. So that gives you some ideas on how you do these kind of big scale things. So if you looked at just the box, you will see the change in land sea flux, and you'll see these other production. We don't incorporate consumption in these grand totals because that is not part of the total. It's a consuming thing. So you see 72.6 and 337.6, and how it's gone from 1950 to 2010. And that's how you get these two numbers at the very bottom in the lower right-hand corner in the Anthropocene. So the next part of the talk, and a much quicker part, is looking at global change, climate change. And here we're talking about storage of extra solar energy in either the atmosphere, the land, or the ocean. And we know how much we produce through greenhouse gases, but because of the way the feedbacks work, we are storing way more energy than we are producing from these greenhouse gases by more than an order of magnitude. And that's mostly being soaked up into the ocean. In fact, so much energy is being put into the ocean that we are getting half of the rise in the ocean is sea level from the steric effect, the thermal expansion. The other half is also thermal, but it's from the melting of ice caps and iceberg production and ice melt from glaciers, etc. From a sediment point of view, because this is a talk on sediment, we know that as you increase the basin temperature, more of that sediment gets into the river channel and gets carried by rivers. But if you were to analyze it in detail, you would find that the greatest amount of change will happen in either the Arctic regions or the high mountain regions, where 1 or 2 degrees could be really change the amount of sediment being liberated and transported. And this is a paper that was just accepted recently in Science. And I'm one of the authors, so I'm showing this even though it's still not in print. And you're looking at two things. In blue, you have the percent increase over the last 70 years of water flow, and largely from melt of these snow fields, permafrost areas, glaciers. And in brown, you're looking at the increase per decade of sediment. And so you will see that these even though there's more water being released, there's way more sediment that's being released. And so it's a rapid flux of sediment being sent down the river systems, in this case from the Himalayas. The same thing goes for Greenland. We never used to model or even understand what was going on in Greenland, but now we include that in our modeling. And here's an example where the entire island of Greenland is being studied, surveyed, often with satellites in the air. Often with satellites from the air. And we can see that there are hot spots, and there's a lot of sediment that's being released, because look at the volumes of ice being melted. So you have 5.6 teratons since 1980 in Greenland, and another 5 teratons since 1980 in Antarctica. So a lot of water, a lot of sediment getting released. You also have sea ice getting reduced, shrinking, and to the tune of about 275 gigatons per year. And what that is doing is that it's affecting the melt and erosion of Arctic coastal zones that are now rapidly retreating, again, producing sediment into the ocean. I think I've only got 1 or 2 slides left. And I just want to take a moment and walk you through this little area, because this is saying that we are tracking where we're getting more water in any given year and where we're getting drier conditions in any given year. If you get more water on easily erodible areas of the landscape, in this case, in the Ganga Valley, you'll get more sediment release. So it's very important to know, as the climate is changing, where that water is falling and how it is changing the dynamics of the river systems from one area to the next area. Also, we're just getting enormous numbers of growth in the number of fires and the size of the fires. And each of these fires, especially if they're in highlands, they release a lot of sediment. And as I said earlier, desertification, in other words, the areas that are getting drier are getting way drier, and they're releasing a lot more aeolian sediment into the ocean. And so we have to take that into account. And we're just starting to work on that. When it comes to what the impact is in the coastal zone, it's enormous. And so really what's happening to a coastal zone depends on how much sediment aggradation gets to that coastal zone. That's from usually fluvial rivers that transport sediment, bed load, suspended load. How much of that is compacting? How much subsidence are you getting? Is there any changes in isostasy or tectonics? And what is the sea level rise due to eustasy? And you put it in these very simple equations, and you quickly can understand that we're sinking deltas all over the world. And in this video, each image is a year from 1984 to 2012. I should update this. And you can see that this Mississippi Delta is sinking right in front of your eyes. And there may be reasons for this other than sediment reduction, even though there is great sediment reduction, but it could also be from oil and gas mining, or in many deltas, it's water mining is the big culprit. But whatever these sources of forcing functions are, you're getting deltas all over the world disappearing. And a final part of this story is that as you change the river temperature dynamics, the thermodynamics, you're actually changing how particles are held in suspension. So in this diagram, you can see that a change of 10 degrees centigrade of river flow can impact the settling velocity greater than a 10-degree change between 25 and 35 degrees centigrade. So it not only depends on the magnitude of the flow, but it also depends on the where this change is occurring, whether it's warm temperatures or cold temperatures. So I'm going to skip this, and maybe I can just show you this diagram. This is the Mississippi River, and we're now able to incorporate dams in these models. So when we're modeling bed load and suspended load, and we start including dams and the sequestration of sediment in the dams, you can see how it in fact impacts both the bed load, that's this brown dotted curve, the suspended load, that's this green curve, and you can see how that impacts both the proportion of bed load along the Mississippi and how the river slope is being impacted by these dams. So in this case, the Mississippi is a greatly engineered river system. If you were to look at the Amazon, on the main stem, you don't have these dams yet. So here you have almost a perfect relationship between bed load proportion and river slope, because you're not getting these engineered changes to the river itself. It's a very natural system. Now, it's not natural in the sense that you're deforesting the landscape and you're releasing a lot of sediment. That does happen, but you don't have this great impact of dams that are affecting many of the rivers of the world. So we're learning how to do this. It's important that we learn how to do this, learn how to model it, so that we can make proper decisions on how we understand the behavior of river systems and their fluxes of sediment to the coast. And I believe this is my last slide. I'll leave you with this up. So when I entered this study way back when, I was not interested in human disturbance of the landscape. I was really interested in how the earth operated, how nature operated, how rivers either linked up to mountains or they didn't link up to mountains, whether they were carrying a lot of sediment or they weren't carrying a lot of sediment. You know, what was the impact of vegetation and things like that? Well, that may be interesting for those of you who are true geologists and study the geological past. For those of you who are more in the modern world of engineering or sedimentology, I think you really have to understand the role of humans in all of its manifestation, whether it be in producing sediment, consuming sediment, the mining of riverbeds, where dams are being placed, because that's the true story of today. That's the story of the Anthropocene. So when you look back at the original slide, my first slide, you need to understand that you're not just in this world of 22 gigatons going to the land, or maybe today it's only 17, but you have to more understand that we are now moving around almost 337, that's close to 700 Great Walls of China per year. So that's per year. That's like circling the globe, I don't know, almost 1,000 times per year. We really are changing the very way we are interacting with our terrestrial environment. So I will leave it at that. And if you have any questions, I'll be happy to try to answer them. Thank you. Stop sharing my screen. There. Did you even hear that?
Perfectly
is anyone still
on
there?
the sediment cycle. It was quite comprehensive and detailed. So now we have time for the question of the public. So to the all, please remember to send your question using the chat. Okay. We have the first question from Oscar Alvarez. Well, in the meantime, because there is some is a little bit slow. I have one from my side. You mentioned many times the importance of considering the human perspective on this budget, on this balance, and nowadays there is a huge motivation on removing dams, mainly in the United States. I mean, in the perspective, there is the idea to remove dams, and sometimes in the human history, some things that looks positive from an initial perspective turns out in bad things, you know. So yeah, so because probably remove all this amount of dams can have a strong response in river mouth stories according to the morphological response on things like that. But the question is, what would be the effect of a massive plan of removing dams everywhere?
Okay, that's a really good question, and I have an answer for that. It's a question that I've asked myself, so I had to think about this. So we know one of the most interesting studies in these big global studies is by a colleague of mine, Bill Hay. And Bill Hay determined what the quaternary sediments, how much of that quaternary sediments made it into the ocean over the last couple million years. And he said about 74% of the sediment from the terrestrial landscape made it into the ocean, and about 26% was left on the landscape. So there's always sediment left on the landscape. And that's a very good number. So if you were to take and say that, okay, so if we removed all the dams, how much of that sediment would hit the coastal ocean? So we could say 74% based on this previous study. That's pretty good. So that means that the other 26% is going to be stored in floodplains. It's going to be stored in lakes, and it won't necessarily, all of that sediment from dam removal won't all get to the coast. But even if the 74% gets to the coast, that's 74% times 65 gigatons per year. Well, natural rivers only are moving, even in the best days, we're only moving around 20, 22 gigatons per year. So I can't do this in my head, but 74 times 65 is what, 50, something like that. So if we removed all the dams, our coastal zones would be flooded with sediment. Even if some of it was stored along the way, we would still be flooding the coastal zone with sediment. Now, maybe that's good for certain environments. You know, a lot of countries, especially in Asia, they like the coastal zone. So they would actually build out their infrastructure, their coastal cities and things like that with all this flooding sediment that would reach the coastal ocean. To them, it would be a good thing in certain circumstances. But if you were a harbor master who was responsible for dredging estuaries and harbors and things like that to get ships in and out, you would not want to see all this sediment come flooding down the system. So there would be winners and losers, and that's almost always the case, that there's winners and losers in our decisions. So you might find that people who like fisheries, they would love to remove all these dams because the fish would go up and down so much more easily. Correct? So again, reasons to remove, reasons to keep, but no matter what, I could say with no hesitation that there are some people whose livelihoods would be killed. People who are farming for shrimp or oysters or things like that. If they were having to deal with all this river sediment coming down, all of a sudden they couldn't do their job. So yeah, winners and losers, as always.
Thank you, Professor. There's a question from Oscar Alvarez. Say, many thanks, Professor Sibisky, for such an impressive summary of the sediment transport rates worldwide and the tendency. Your research always has been very motivating. I have a question. What is being more important in coastal retreat at global scale currently? Sediment retention by dams or sea level rise?
Yeah, that's a very complicated question. Because if you said, well, what if humans weren't around and we didn't have these dams? Well, then sea level rise would win out. But at some level, if you have, when river sediment gets down to the coast, it's the great energy buffer. It buffers the ocean energy. It basically eats it up. It takes so much energy to move sediment. So if you keep supplying river sediment, you won't get much coastal erosion as long as you don't stop that sediment from getting to the coast. It's a perfect buffering system. So you stop that, you're going to get coastal erosion. Now, we never are going to take out all the dams all at once, and and so it's almost a theoretical construct that you're asking me to answer, because if you said, well, if you took out the dams on this river system, what would happen? I might be able to actually tell you which would be worse, the sea level rise from global warming, or the loss of sediment because of the dams, or the gain in sediment from the loss of the dams. So I think it's on an individual basis that you can make this, because I don't have a magic wand to either create the dams or take them out all at once. But I do know from the dams that we've taken out in the US, most of that sediment gets down to the coast much faster than we anticipated. We thought it would get moved like train cars. It would, you would move it so far in 1 year, and then the next year's flood, it would move down another distance, and it would keep marching down towards the coast. There's scientific evidence for this slower marching, but where we've taken out these dams, we see that it gets to the coast rather quickly, way faster than we anticipated. And so in effect, you have a new flux of sediment on the coastline that then takes many years for the coast to reshape it back to where it was. It may take a decade or two. So you're dealing with lags in the system. You have the lag of the river and its flux, and you have the lag of the coast and its flux. And again, in each coast, because the tidal energy or the wave energies are not the same, it's really a unique situation. And although we can probably answer the audience's question theoretically, I don't think that has much relevance. We would have to look at locally the environmental conditions and the river system itself to really get a handle on, oh, in this river, even if we took all the dams out, you still wouldn't have enough sediment to cope with sea level rise. Okay. Or in this river, yes, certainly you could prograde the system out another 10 kilometers, and it will take another 50 years for it to march back to where it is today. And that tells you sort of the scale of who's winning and who's losing over a period of time. So it's a complicated question, and I hope I've answered it.
Okay, yeah, right. Another question, this is from Gerardo Perillo. Many thanks, Yaya, for your presentation. Nice to have you in PiA. Most values you are presenting is about of the last gouging station of the river. What happened at the stories? How much of these sediments are being retained?
Ah, Gerardo, my friend. Yeah. So I don't think, for the story I told today, it's probably generally true without needing to answer that question. You know, from a geological perspective, you can't store too much sediment in an estuary. Otherwise, you would have a mountain of sediment there that wouldn't make sense. But certainly the flux of sediment entering an estuary or entering a delta, we know pretty well, both from monitoring and also from modeling. And how much of that sediment gets across the estuary or gets across the delta, that again is like the last question. It's very, I would say, site specific. So for instance, many deltas have distributary channels, and many countries don't like their deltas to be flooded because they have these big mega cities on the deltas, and they don't want the river to flood the delta, the landscape. And because they don't want it flooded, that sediment isn't getting deposited on the delta, so there's very little trapping. That sediment shoots out, it enters the delta and shoots out to the coastal zone where it's released. Some of it is retained in the channels, and that retention in the channels, like the pole channels, are there a grading, growing vertically. The riverbed is growing vertically by many centimeters per year. It's very rapidly aggrading to the point where the channels are now super elevated 2 to 3 meters above the surrounding plain. So and again, you can see from a geological perspective, you can't do that forever, because you now would be changing the slope of the river system. The hydraulic head would have to change. So you can't do that forever. And so you will eventually get flooding of the landscape. Estuaries are a little different because you can get trapping, tidal pumping, and other things like that that can retain sediment. So in that cases, you could change estuaries into deltas from changing the flux of sediment. And we know that's occurred geologically when we went from basically when sea level stopped rising during about 6,700 years ago, you got the development of deltas. So we know that this kind of change in sea level and change of flux can really affect whether you have deltas or estuaries. So, but if Gerardo, if you're talking about the next 50 to 100 years and you're not talking about geology, yeah, I think that you're going to get, depending on the estuary, you could get a lot of trapping of sediment in the estuary itself.
Okay, thank you. This is from Francisco Guerrero. Thanks, Dr. Sivitsky, for your presentation. Have you gathering chemical information about this sediment? I wonder about the implication of your findings in terms of particularly carbon fluxes.
Okay. So now you're asking
got all the difficult questions.
Now you're asking me a question that I know a little bit about, but I'm not a global expert.
Yeah.
So what I know is that one of the easiest ways for a scientist to determine what the carbon flux is to measure the suspended sediment. And they measure the relationship between carbon and the suspended sediment. And at a global basis, they take these relationships either at the continental level, and they create basically a carbon yield for that continent or region. And they then keep adding these up until they cover the entire world and they get a global flux. That's different than how we do it. We're actually modeling or measuring all of the rivers and their particles in a global system. So since carbon is putting so much of its determining side on the sediment, particulate matter, it's hard for us to really get an understanding of the mechanics of this all.
Yeah.
And furthermore, you have very unique sides of carbon that we just don't have when we're dealing with particulate sediment. For instance, a lot of the carbon that's released into the river systems of tropical rivers, they get converted to gases before they reach the coast. So they have a way of getting out of the rivers along the pathway of the rivers. And while we don't have that, well, we have sequestration in floodplains, and we can sort of use satellites to look at the scale of the flooding on the landscape and how much sediment from the overbanking. So we can do a little sequestration, but we don't ever have to contend with gases and the conversion of particulate carbon to, gases and things like that. So I would say, though, the experts on carbon are a little further behind those of us who work on particulates because they have more complexity within the system.
Okay, Professor, thank you. Another question, this one from Francisco Pedocchi. Thanks for your presentation. Do you have any comments on possible feedbacks, positive or negative, between the sediment transport changes and climate change?
Feedbacks. So I think that's the important word. And I guess I really didn't talk about feedbacks. So just as an example, this is a stupid example, but at least it's an example. So there's more freshwater discharge into the ocean from Greenland via icebergs than from meltwater. So the volume of fresh water entering the ocean from Greenland is mostly by icebergs. So one feedback will be is that when these tidewater glaciers are no longer on the coast, but they're now melting back on land, you won't have any icebergs from that mechanism. You will simply have meltwater. It'll all become meltwater. And so icebergs from Greenland can drift for a couple thousand kilometers around the North Atlantic, as an example, or around Antarctica. So in those cases, that, especially for Greenland, maybe in a few hundred years, that will disappear. So there's a feedback on a process as an example of, if you were to run this experiment for 1,000 years, what would be the changes? And often people do that just to understand. Usually we do that to see if a model blows up. Because you push models to look for weaknesses in your logic. And that would be a good way to look for feedback on our logic. So another thing would be, a feedback would be is that we're finding there's more aeolian sediment getting onto ice surfaces. Our ice surfaces, like on Greenland, they're getting darker and darker and darker. So they're able to soak up solar radiation. And so that feedback would allow greater melt, because you're soaking and absorbing albedo effects, you're absorbing the solar energy. So that's one example. Another example, but maybe you weren't talking about this in climate change, but is we're producing so much plastic now, and we're seeing in turbidity currents and gravity flows, debris flows, we're seeing large amounts of plastics incorporated into these flows. Well, these plastics have a buoyancy that's different than a normal sediment. So they will change the mass buoyancy of the nature of these sediments. So that's a feedback. But you're talking about climates per se, and so I'm going to have to put my thinking cap on to think about all the climate dynamics. Okay, here's the feedback. You cut down the forests of the Amazon. There's still a lot of Amazon forest left. But if you were to cut it back, the feedback would be on decreasing the precipitation, because it's the aerosols from the forest itself that provide the nucleus for the water molecules to coalesce around in the formation of clouds. So that would change. If you change how the water droplets formed, you would not only decrease the levels of precipitation, but you would decrease the intensity of the precipitation. So there's a feedback. I don't think you want to run the experiment to have a drier Amazon, but potentially that's where we're headed. That feedback is particular for tropical forests. So the boreal forests don't have that feedback. There's enough sediment in the atmosphere that the nucleation of these water droplets are increasing because it's getting dustier in the air. And so if there's any water moisture, it will more readily form around them. So it's not a global phenomenon, it's a regional phenomenon, but I'm using that only as one example. But if you could think along those lines, you may come up with a list of feedbacks on our behavior and how they would impact whatever you want to impact, whether it be precipitation, ice fields melting, snow fields melting, permafrost, things like that. Like, for instance, I guess this is another feedback, in the polar regions, a lot of the permafrost traps methane in its soils. So if you melt the permafrost, the feedback there is to release methane, which is a very reactive gas that then would speed up global warming. And so there's a very positive feedback cycle. So I don't know. I would assume that if there was 10 of us in a room, we could probably come up with a list of things that would be interesting and worthy of study.
Okay, thanks, Professor. I have two more questions. This is from my good friend Bernard Becker-Ehrenbrink from Woodsville. Hi, Jaya. Has the fraction of human energy use that is expanded towards moving sediment change between 1950 and 2010? What fraction of our overall energy consumption now goes to sediment movement?
I haven't done that. It's a quick answer. I don't know. We have a really good understanding of energy consumption, human energy consumption. We have a really good energy. In fact, because of the interest in global warming, this is a solved problem. And yes, there may be some small areas that still require a lot of consideration and thought. But in general, we understand humans and their energy consumption. And most of the countries that are part of the United Nations, they are providing the data on their energy consumption of that country. And what we're less sure of is where it's going, how it's being used. So if someone was to say, well, if you had a tractor and it was moving, I don't know, how many tons of sediment per hour, and it took the human who's driving the tractor so much energy there, so many kilojoules per hour, and you were looking at the fuel that the tractor was used and the fuel that made the tractor and repair the tractor from time to time, you probably could work out for that country, that situation, what the energy consumption of moving X tons of sediment would be. And if you were to do it in a logical way, you could probably scale that up for the world. And so you probably could get a handle at what that energy consumption is. But what I do know is that most of our energy consumption is going to moving sediment. And that's from constructing megacities. I mean, there's only so many ways you can use the zettajoules in a year that we're now seeing happening on a regular basis. You can use it for building megacities. You could for mining, for all sorts of construction, infrastructure. That's your big use of energy. Transportation is an energy consumer, that's true. And you would have to take that into account. But building airports, train systems, roadways, to run that infrastructure still is largely in the sediment moving world. So I think you could take the diagram that I've given you, and someone who's interested in this probably could start converting all of those numbers to energy consumptions. And we probably could get a number of the total human energy use, how much of it is going to moving sediment.
Okay, great. Thanks. And this is the last one. It's come from Julian Estrada. Thanks for the presentation, Professor Sibisky. I have a question. How does this affect coastal wetlands where small rivers flow, because the direction of the flows change in this river's mouth.
How does what change?
Yeah, I think he's referring to the changes in the sediment cycle, how this is affecting the coastal wetlands, not just the estuaries and deltas and the coastal retreat, but also the wetlands, the coastal
Okay.
lagoons.
So, yeah. So I would imagine wetlands typically, they're not associated directly, but indirectly with large rivers. And a lot of the wetlands around the world have much smaller rivers that are feeding them. And typically we don't dam small rivers, or if we do dam small rivers, they tend to be small dams. And these small dams, so these small dams tend to not retain as much sediment. So they retain some of the coarser sediment, but a lot of the finer sediment, the wash load, that it enters the reservoir and then it leaves. And the way they're constructed, these smaller dams, you're not damaging the turbines like you are on the large dams that really have to take the amount of sediment that passes through the turbines into account. So I would assume that damming and wetlands aren't nearly tied directly, only indirectly through the bigger river systems. So now you've got changes within the hinterland of the wetlands in terms of, is there human activity in that hinterland that is generating sediment, or in some cases reducing sediment, because there's many human activities that can also reduce sediment. So you would have to examine that from a very local perspective, and so you can speculate that it can go either way depending where you are. Sea level and its impacts are affected by wetlands have a unique ability to try to keep up with wetlands. So they will, as sea levels rising, they will redistribute their plant material, their species, their everything, so that they can try to keep up with that growth. Eventually they'll fail and you'll get a retreat inland. But there is a unique biological feedback system that's going on that will try to slow down the destruction of the wetland. I think if I was to add a comment here, I would say is that typically it happens at a threshold. And that threshold we don't really understand. And the threshold is there because we don't have the energy in that wetland that's equal every single day. We have winter storms that can be very high energy systems, maybe even more so, more destructive than hurricanes and tropical storms. And so you've got these winter storms will reach a point where one of them, if it's particularly bad, will change the root structure nature of the growth of these wetlands, so that the development of the wetland will not be like it used to be. It will be a changed system. That we have a very poor understanding of. We have evidence for it around the world. And I know that people are really putting their heads behind this because it is so important. You want to know, I mean, one of the biggest problems with wetlands is the role of freshwater versus saltwater in the pores of the sediment itself. And you're changing the hydraulic gradient of both with the sea level rise of that salt water being pumped into the land versus the fresh water in the land. So depending on the very nature of how freshwater or rainfall is changing in that area versus sea level rise, you end up with complexities that we still, I think, are working our heads around. But it is one of the worthiest questions and topics to work on, definitely.
Okay, thanks. Finally, we got a message from Marcelo Garcia. A great conversation, Professor Sibisky. Remember that the wash load becomes bed load via flocculation in the estuaries and deltas. That's the message. Well, Professor Sibisky, we really appreciate your time, effort, and willingness during this lecture. It was quite amazing and impressive the way in which you present this number, this budget, many facts, many things to think about it. So we appreciate really much. We thank you for everything, and we thank all the attendants for joining us during this talk. And well, that's all, and we expect to follow us next month during the next webinar. So, well, thank you, everyone. Professor Sibisky, thank you very much. Bye-bye.
Bye.
Los siguientes contenidos de Uninorteco te pueden interesar. No olvides suscribirte a nuestro canal.